Sending humans to the moon is an incredible feat, but surviving the trip back, that is a brutal, calculated gamble against the laws of physics. Before we break down the terrifying realities of atmospheric re-entry, take a second to hit the subscribe button and share this with your fellow space fans. When the 4 astronauts aboard the Artemis II mission return to Earth, their Orion capsule will hit the upper edge of our atmosphere, traveling at a blistering 25,000 miles per hour. That is roughly 11 kilometers in a single second. At those speeds, air molecules don't simply move out of the way. The atmosphere acts like a dense, solid object. Hitting the air at Mach 32 is the aerodynamic equivalent of slamming an airplane directly into a cement wall. This animated diagram illustrates exactly why their approach angle has to be flawless. If the capsule comes in even slightly too steep, the resulting friction will completely incinerate the spacecraft and everyone inside. That is, the angle is too shallow, the capsule will ricochet off the dense air like a skipping stone on a pond. With no fuel left for major course corrections, the crew would be flung outward into a deep space orbit, trapped with dwindling oxygen and food. The crew has exactly one single shot. They must bleed off an immense amount of kinetic energy, relying on nothing but the Earth's air to act as their brakes. To manage this, NASA utilizes a technique called a skip re-entry. As this diagram shows, the capsule dips into the upper atmosphere, rises back up to cool off, and then takes a second final dive. This splits the extreme heat and deceleration forces into 2 distinct, survivable phases. Even with this bouncing maneuver, the capsule compresses the air directly in front of it so rapidly that the gas doesn't have time to exchange heat with the surrounding environment. The temperature immediately around the ship spikes to 5,000 degrees Fahrenheit. That is half the temperature of the surface of the sun. The only thing standing between the crew and that lethal heat is an ablative heat shield made of Avcoat. It is purposefully designed to melt, turn into gas, and erode away. As it sheds material, it carries the extreme heat off the ship. During the unmanned Artemis I test flight, engineers discovered that this erosion was somewhat uneven. If a localized weak point forms during descent, hot plasma could breach the hull. To prevent a catastrophic failure during Artemis II, NASA engineers are altering the capsule's approach angle to ease the intense stress on the shield. The safety of the crew ultimately depends on the carefully calculated partial destruction of their own ship's armor. If it doesn't burn away precisely as planned, they vaporize. At peak friction, the violent collision of air molecules actually strips electrons from their atoms. This envelops the descending capsule in a thick layer of superheated ionized gas known as a plasma screen. This plasma is completely impenetrable to radio waves. For 7 agonizing minutes, Mission Control experiences a total communication blackout. They have absolutely no way to know if the capsule is intact until it slows down enough for the plasma to dissipate. Inside the cabin, the crew endures their own silent ordeal. The immense braking forces required to slow down from orbital speeds will subject these 4 astronauts to gravitational loads peaking at 8 Gs. Under 8 Gs, your body weighs 8 times its normal amount. It feels exactly as if a baby elephant is sitting on your chest. Your lungs are compressed so tightly that pulling in a single breath takes immense physical effort. If you're fascinated by the intense realities of spaceflight, make sure to hit that subscribe button to catch more deep dives into the science of space exploration. At an altitude of 26,500 feet, an automated 4-stage system takes over. 11 massive parachutes deploy, violently yanking the capsule's remaining speed down to a survivable 20 miles per hour. The crew must silently endure extreme physical compression and total isolation, waiting to see if their engineering holds up. And even when the parachutes open, the danger is far over. The Orion capsule concludes its journey by plunging into the Pacific Ocean, but water does not compress easily. At high impact speeds, it acts like a solid surface. If the capsule's angle is off by just a few degrees when it hits the water at 20 miles per hour, the resulting shockwave could easily crush the hull. Once they splash down, there is a serious risk that the capsule could submerge upside down, leaving the crew hanging inverted in their seats. To counter this, a set of specialized balloons automatically inflates on the roof of the capsule, forcing the heavy craft back into an upright position. Even floating peacefully, the crew is surrounded by a hidden chemical threat. The spacecraft's thrusters run on highly toxic propellants like hydrazine. If the violent impact of splashdown damages the fuel tanks, those toxic fumes could leak directly into the sealed cabin while they wait for recovery. And the astronauts are in no condition to rescue themselves. After spending days in zero gravity, a sudden return to Earth's pull wreaks havoc on their cardiovascular systems. Blood pools rapidly in their legs, inducing extreme dizziness and effectively paralyzing them. They cannot stand up, much less climb out of a bobbing spacecraft alone. This is why their survival ultimately hinges on a massive, highly coordinated United States Navy operation. Medical and recovery teams must rapidly secure the perimeter, test the air for toxic gas, and physically extract the incapacitated crew from the capsule. Coming home from the moon is not a gentle victory lap. From the very moment they hit the upper atmosphere to the second they are pulled from the water, it is a brutal, hyper-calculated fight against the laws of physics, pushing the absolute limits of human endurance and engineering. Thank you so much for watching.